right, for those of you that are on Zoom, please type in the chat that you are here. For those of us that are physically present, I'll be circulating our roll sheet right now. All right, so I see at least one of you has already noticed that something's been posted with regard to Project 2. So let's go ahead and take a couple of minutes to talk about that. Your BJT project options are available on our course's Moodle page under the project number 2 link on the side there. I believe you have 5 options. The first of which is a boost converter. A boost converter, let's see, it says is a switching regulator because it requires an external oscillator to function. You are not expected to design the oscillator yourself. You're just supposed to use a pulse source to generate a square wave. Your design must boost the input, let's see, the input voltage is steady, ideal 3.3 volts. The output voltage is 5 volts, and the load is expected to draw between 500 milliamps and 1 amp. So that gives you your power constraints and all that kind of good stuff there. So you're stepping up that voltage from 3.3 to 5. All right. And it asks you to try to get the ripple below 25 millivolts. The next option is an AM modulator using a BJT. Create an active biasing network in which a message signal controls the amplifier transconductance. Then the carrier signal is applied at the amplifier input so that the resulting output is an amplified more, let's see, when the message value is higher. The result is the amplitude of the output wave corresponds to the amplitude of the message input, but the frequency of the output wave corresponds to the carrier wave's frequency. So you're building an analog mixer really here. Carrier wave frequency of 200 kilohertz, approximately a linear modulator, which means the message is directly proportional to the modulated signal amplitude. The message is to be used for voice modulation, and the output should be around 4 kilohertz. All right. And we have a Zener regulator with an emitter follower. Emitter followers we're not going to talk about until probably Friday or Monday. Let's see. Designing the portion of a power supply which reduces the variation from a rectifier stage 300 watts at 48 volts DC to an RF transmitter. The transformer stage transforms a 3-phase AC power source from 120 volts RMS to 50 volts peak to peak, which is rectified before being applied to your circuit. The input to your circuit is guaranteed not to fall below 48 volts DC, but may vary as high as 50 volts. Let's see. Use a Zener and a BJT. All right, then we have a buck converter. So that's the opposite of a boost converter. So if a boost converter steps the voltage up, a buck converter is stepping a voltage down. So, and then lastly, we have a logic gate. So expanding on the logic gates that are available just using diodes. Here we're going to introduce an inverter, which switches a signal from a positive value to a negative value, or from on to off, etc. All right, so those are the 5 different projects. We'll get into more detail about some of those things in a little bit. I'm not sure what due date I want to have on that. So let's talk about dates in this class for just a smidge. Let me make sure what's going on here. Okay, just people saying they're here. So, after talking with Dr. Batari at length, we are significantly ahead of him. So he's not going to be able to finish what he wants to talk about until Monday at the earliest. So that means the exam will be next Wednesday night. So February the 3rd is when your night exam will be. We have most of the exam already made out. We are still in deliberations about the equation sheet. And so what I mean by that is we are deliberating whether to give you an equation sheet or to allow you to just bring your notes and go for it. I'm not partial one way or the other. But yeah, we should have something decided on that by Saturday so that we can get, if we choose to go the equation sheet route, we can get that to you over the weekend. You'll have a couple of days to look at it and things like that. So to be clear, our exam number 2 will be held on Wednesday, February the 3rd at 6 p.m. in a room to be determined. We're trying to get the same room as we had last time. We just have to make sure it's available. This exam will cover all of the material that we covered in chapter 4 and in chapter 5. So chapter 4 was all about BJTs and effectively large signal analysis of how we bias them and all that kind of good stuff. Chapter 5 is all about using the BJT as an amplifier, where to this point we've talked about input resistance, output resistance, and voltage gains as kind of theoretical quantities. And then we've gone through specifically common emitter amplifiers and determined those 3 parameters in various biasing states and all that kind of stuff. So any questions about what's going to be on the exam? The last 2 large topics that we're going to cover are common base amplifiers and common collector amplifiers. So once we get done with those, we're finished. Any questions, comments, concerns? All right, so before we move along today to the common base amplifier, I'd like for us to take some time to actually work a numerical problem because I've been kind of avoiding them because I thought we were behind and it turns out we were ahead. So yes.
So next is just going to be like when we started BJTs.
So when we started BJTs to when we finished BJTs on Monday, it's all BJT circuits. Let me see, I think I might have something else in chat here. Somebody's asking, repeat when the exam is. Yes, the exam is next Wednesday evening at 6 p.m. I do not yet have a location for it, but we are trying to get the same room as last time, which I believe was IESB 318 or 316, the big chemistry lecture hall. So trying to get that one, not sure if we'll have it yet, working on that today. All right, so let's start today then by working a problem I feel is very representative of what you may find for a common emitter circuit on this. If anything, this one might be a little bit harder than what you should expect to see. So let's say that we have the following circuit. Make sure I'm on page 1. All right. So this is the circuit of interest. We're going to be working with beta is equal to 100. And speaking of that, oh, Vitaly's, I think he's in Zoom. But there was a question about one of the homework problems where beta wasn't specified. And if you look on the front page of the homework set, it tells that if beta isn't given, always assume it's 100. So just wanted to point that out because Dr. Batari had to point it out to me. I couldn't figure out where it was either. We have an IS of 10 to the minus 16 amps. VA is equal to infinity, so we can neglect the early effect. And our ultimate goal in this problem is to get a numerical answer for the voltage gain of this circuit. Okay. So this guy looks pretty gnarly, probably looks like an unfamiliar topology to you. Would that be a fair assessment? Have you seen anything like this, do you think? Probably not, right? Okay. So what we're going to do, we're going to break it up into two distinct portions. A large signal circuit through which we can do our large signal analysis to determine the bias point, which is going to then allow us to calculate the transconductance and the value of our pi. And then we're going to do small signal analysis using those values to determine the voltage gain. It's always going to be a two-part process whenever we have an amplifier circuit, right? We need to determine its operating point, which is large signal analysis, and then we need to do small signal analysis to determine voltage gain or input and output resistance, things of that nature. So let's look at our large signal model first. So the first thing I want to point out here is that we are assuming that we're operating at a frequency where in the AC analysis or the small signal analysis, all of our capacitors are going to behave as short circuits. But when we're doing our large signal analysis, that is, again, a DC circuit analysis, which means all of our capacitors should behave like open circuits. So what does that do to this circuit? If this guy right here becomes an open circuit, that's disconnecting that 50 ohm resistor from influencing the bias condition of this guy, right? If we open circuit this guy, that's putting that 12 kilo ohm resistor and that 8 kilo ohm resistor in series. And if we open circuit this guy, that's putting that 200 ohm resistor and that 50 ohm resistor in series. So we could redraw our circuit as follows. We have a 2.5 volt source. Here's our 1 kilo ohm resistor. Here's our emitter resistance. It's going to be 250 ohms in total. Then we have a 20 kilo ohm resistor right here. This current is my base current. This current is my collector current. And here I have my voltage VBE. So this is what our large signal model looks like. Does anybody have any, or excuse me, this is what our circuit reduced using our DC or large signal parameters is going to look like. Does anybody have any objection to the way that I've redrawn this? Does anything not make sense? Let's start there. Cameron, what's up? Right. So when we open circuit that guy right there, that takes that guy out. Now, because the VN represents the small signal that we are trying to amplify, it's actually very good that we are disconnecting that, because that would be considered a short to ground because we're working this effectively using superposition. So it will be turning off that VN voltage source. Yeah. Yes. So right now we're doing the so large signal, all of our small signal sources are turned off. Only our power supply voltage is effectively left on here. And if we had any batteries or anything like that in the circuit, we'd leave them on too, but we don't. So that's why VN is gone. Again, open circuiting the capacitor C1 places the 12 kilo ohm resistor in series with the 8 kilo ohm resistor, which is where this 20 kilo ohm resistor comes from. And opening circuiting the emitter capacitance places the 200 ohm resistor in series with the 50 ohm resistor, which is why we have a total emitter resistance of 250 ohms. So what kind of biasing scheme is this? Self-biasing, but it also happens to have emitter degeneration, right? So we are going to start our analysis by looking at our self-biasing. So let me see real quick here if I can happen to find those notes. If I save them, if not, we'll go through it real quick. Let's see. Are these they? Let's find out. No. But I'll need those in a minute anyway. No. Okay. I guess I didn't save them for whatever reason. Not a problem. All right. So we'll go through this fairly quickly then. So what I'm going to do is I'm going to write two equations utilizing Kirchhoff's voltage law in this case to determine what this voltage VCE is. I'm going to set those two relationships equal to each other, and then that should allow me to calculate the operating point. So my first equation, I can say that VCE is VCC minus IB plus IC times RC, right? So I'm saying, so I have 2.5 volts. I subtract from that the voltage drop over the 1 kilo ohm resistor, and I will subtract from that the voltage drop over the 250 kilo ohm resistor. So that'll be IB plus IC times RE, and that leaves me with VCE. Anybody have any questions, comments, or concerns about that? Everything seemed fairly reasonable. So I'm just going to simplify things just a smidge here. VCC minus RC plus RE. IB plus IC I can write as 1 plus 1 over beta times IC. So I'm kind of lowering my number of unknown quantities here. So I know everything in that equation except for VCE and IC. I can also write an equation that says that VCE will be equal to the voltage drop over my base resistance. So that would be IB times RB plus my voltage drop VBE. Anybody have any questions, comments, concerns about that particular guy? I'm going to rewrite this one, expressing my base current as IC divided by beta, which gives me then RB over beta IC. That does not look like a good C. Plus VBE. And now I have two expressions for VCE, and so I can set them equal to each other, right? They represent the exact same quantity. So I can say that VCC minus RC plus RE 1 plus 1 over beta IC is equal to RB over beta IC plus VBE. And I'm going to do a little bit of rearranging here. VCC minus VBE will then be equal to RC plus RE times 1 plus 1 over beta plus RB over beta, all multiplied by IC. And I'm going to express IC as IS EXP VBE over VT, which gives me one equation with one single unknown, right? I know what the values of all my resistances are. I know what beta is. I know what IS is. So you guys take a moment to chug the numbers here and then give me a value for VBE. Anybody able to get anything? Just thinking, okay. You got 782? That is not what I got.
709.
not what I got either. All right, well, distinct possibility I might have made a mistake here. Let's see what I did. I used MathCAD. Let's just see. So let's see. I chose a guess of beta is equal to 800, or excuse me, VBE is equal to 800 millivolts. So let's make sure I have all of my numbers correct here. Beta was 100. IS is 10 to the minus 16 amps. My thermal voltage is 26 millivolts. VCC is 2.5 millivolts. All those seem legit. My collector resistance is 1 kilo ohm. My base resistance is 20 kilo ohms. My emitter resistance is 250 ohms. All those numbers seem legit. All right. So let's see. I have VCC minus VBE is equal to RC plus RE. What I'm going to do here is just make sure that I'm explicitly multiplying, because there's a small chance here that it's treating this as some sort of weird function. Yeah. So RC plus RE times 1 plus beta plus RB over beta times IS. So the one thing I want to make sure here, that didn't change anything, okay? And find BBE. So I'm getting 668. I don't see anything wrong with my equation. Let me just use my calculator real quick and see what it gives me. Let's. There we go. Yep. And it should be 1 plus 1 over beta. All right, so let's circle back around to the MathCAD sheet. All right, there we go, 782.453, which I believe is what you guys were saying. So let's run with that number. So 782.453 millivolts. This voltage value will in turn give us a specific collector current. Let me grab my calculator here real quick, because that collector current is what's going to tell us transconductance, and from that then the resistance R pi. So we have 10 to the minus 16 times E to the VBE 0.782453 divided by 0.026. 1.178 milliamps. Does that sound about right? So that's just rounding error. So 1.174 milliamps is what I'm getting on my MathCAD sheet. So, all right, so let's go 1.174. All right, so we now know our operating point, so we can use this information to determine our transconductance. So transconductance GM is by definition IC over VT. Scroll down and find that exact number. 0.045 Siemens. Yeah, I'll just use that then. And lastly, I can get R pi, which is going to be beta over GM, which is apparently 2.214 kiloohms. All right, so we're done with our large signal analysis and have extracted all of our necessary parameters. Now let's move into the small signal circuit analysis, okay? So let's look back at our original circuit here. Now, instead of treating all of our capacitors as open circuits, we are going to treat them as short circuits, right? So if we replace this guy with a short circuit, this guy with a short circuit, and this guy with a short circuit, obviously now our input voltage source is connected to the rest of the circuit. So that 50 ohm resistor is going to be in play. What happens to the 12 kilo ohm resistor when we short out C1? It's not in series with the 50, but it's not in series with anything else either. So one leg will be connected to the base, the other leg will be connected to ground, right? What's going on with the 8 kilo ohm resistor? One leg will be connected to the collector and the other leg will be connected to ground. So it is directly in parallel with that 1 kilo ohm resistor. When we short out our emitter capacitor, that is bypassing this 50 ohm resistor. So we have an emitter resistance of 200 ohms. So let's draw just that. So we will have something that's looking a bit like this. Be in. Here's my 50 ohm resistor. Here is my 12 kilo ohm resistor. Then over here, I have an emitter resistance of 200 ohms. Between my collector and ground, I have 1 kilo ohm in parallel with 8 kilo ohms, right? And then here is V out. So let me just double check I got everything in the place it's supposed to be. So yeah, 1K is in parallel with 8K. 12K is between the base and the ground. Everything seems reasonable here. All right. So what we have here should be fairly recognizable as well, right? Over here on the right-hand side of my dashed line, I have a common emitter with emitter degeneration, where I also happen to have that extra 8 kilo ohm resistance in parallel with RC. So I know what the voltage gain of that right-hand stage is pretty easily, right? So I'm going to call this guy, this voltage right here, VB, On the left-hand side, I have a simple voltage divider circuit, so I can figure out what the gain of that stage is fairly easily. And I'm going to say that my voltage gain is simply V out divided by VB multiplied by VB divided by Vn. Just breaking it up into two discrete stages that we can easily analyze, as opposed to looking at the whole picture all in one go, where it'll be all gnarly and ugly. So if we circle back around to our notes, let's see, we're going to have VB over, or excuse me, V out over VB. So let's scroll through these guys till we find something that looks right. So I guess the question here is, do we want to use the common emitter with emitter degeneration model, or do we want to use the common emitter with emitter degeneration and base resistance? Yeah, so the honest answer here really is that we can use either of them if we can make our input network look like a single resistance, which we totally can. Or we could simply use the common emitter with emitter degeneration as our second stage, and then figure out what the gain stage is in the first. So let's use the common emitter with emitter degeneration scheme, right? So just to be clear, I'm saying that everything to the right of this dashed orange line looks extraordinarily similar to what I have right here. The only difference is that I have another resistance in parallel with RC, right? So if I look at my voltage gain equation for this guy, it's negative beta RC. Let's see. So everywhere I see RC, I'm going to replace that with RC in parallel with that 8 kilo ohm resistor. And then I divide this by R pi plus 1 plus beta times RE. All right, and I should be able to calculate a numerical value for this, right? So let's go ahead and take care of that. So I'm going to have negative 100 times, let's see, RC, which is 1 kilo ohm times 8 kilo ohms divided by 8 plus 1, so that's 9 kilo ohms. Divided by R pi, which we found to be 2.214 kilo ohms. +3. Plus 101, 1 plus beta, times RE, where RE is 200. And I get a gain of negative 3.966 volts per volt. We don't really particularly need the unit. Anybody else get anything similar? Yes, okay. All right. So now we need to develop a relationship for determining the voltage or the ratio of VB to VN. So from the perspective of my input signal, VN, it sees that base resistance of 50 ohms here is my 12 kilo ohm resistance. And then it sees, so here's that node where VB is taken, the input resistance of my transistor amplifier stage, right? So if we go back to our notes, the input resistance of this transistor amplifier stage, or input impedance, is simply R pi plus 1 plus beta RE. And so, using our rules for voltage division, we can see that VB divided by VN is going to be 12 kilo ohms in parallel with R pi plus 1 plus beta RE divided by 50 ohms plus 12 kilo ohms in parallel with R pi plus 1 plus beta RE. So if we substitute in our numbers here, let's do this. R pi was 2.214K. All right. All right, so I have 12 times 10 to the 3 times X. So let's see. Zero 0.994. And so our overall voltage gain is then 0.994 times the gain of the other stage, negative 3.966, giving us an overall gain of negative 3.940 volts per volt. So, anybody have any questions about this? It'd be a big chunk of it, obviously. Cameron, what's up? Pardon? Well, so I looked at it. I mean, so for my, yeah, so when we went to get V out over VB, so I'm splitting this guy up into two stages, right? the right-hand stage has a voltage gain of V out over VB, and then the left-hand stage has a voltage gain of VB over Vn. So I'm analyzing those two things discretely and saying that the overall gain is simply going to be the product, right? Simple algebra tells me that my voltage gain by definition is V out over Vn. So if I can multiply V out over VB times VB over Vn, I get V out over Vn. From there, looking at this particular small signal simplified circuit, so I've shorted out all of my capacitors, and I'm just trying to figure out what it looks like. I can see, if I go to my notes here, that it looks like my common emitter with degeneration, where in the small signal realm, this VCC is grounded, right? To small signal, we turn off that power supply. So I have a BJT transistor with some resistor placed between the collector and ground and some resistance placed between the emitter and ground, which is exactly what everything to the right-hand side of the orange line here looks like. So that's why I used that voltage gain that we've already determined, right? The only change I needed to make was recognizing that RC was these two guys in parallel. For my gain analysis for the left-hand stage, it's a simple voltage divider, but I'm looking in through the input terminal, right? And so I see that 50 ohm resistance and that 12 kilo ohm resistance, but I'm also going to see the input resistance of my transistor amplifier. And I got that from where we literally use the small signal model to determine the input resistance of my small signal amplifier. So when I'm looking at my first stage, its gain characteristics, I'm just treating my second stage by its equivalent input resistance, because that's what I would see looking into that terminal. And working the problem in that way, as opposed to drawing a small signal model for everything with all of the different parts connected, should be significantly easier. Looking at it from a stage by stage perspective should be significantly easier than looking at everything all at once. It's kind of like how when we had cascaded op-amp circuits, right? If you could identify that, oh, this portion is an inverting amplifier and this other portion was a non-inverting amplifier, that made things a whole heck of a lot easier than having to do the big nodal analysis equations where we treated everything as on at the same time. It's the exact same principle. All right, and any other questions with regards to this example problem? Exactly right. So I simply multiplied 0.994 times negative 3.996 and got negative 3.940 with a little bit of rounding there, obviously. Everybody? Well, apparently MathCAD didn't help me too much. Just screw something up anyway. But yeah, they're very doubtful that it will allow you to bring a laptop. We would break a problem, like on the exam, this would be broken up into multiple different parts. So for example, one problem would be calculate the biasing condition. And then the next problem, just in case you missed something on that, would be like, assuming IC is this, then calculate the voltage gain kind of thing. So we're going to test whether you can do the individual parts, but we want to make sure that if you make a mistake on one part, it doesn't influence the outcome on the other part. I think is how we're approaching it this time. And like I said, I'm not 100% sure whether or not we're going to be able to, whether it's going to be a equation sheet or just allowing you to use your notes, but we'll get back to you on that as soon as we argue further. can figure something out there. All right, we have about 20 minutes left. So let's jump in very briefly and talk about the core common base amplifier. All right, so common base amplifier is one at which we have power supply voltage. We're still going to have some collector resistance. We're going to take the output at our collector terminal. Now we are biasing our transistor with a fixed base voltage. So, and then lastly, we are applying our input at our emitter terminal. So anytime we see that the input is applied at the emitter and the output is sensed at the collector, that is a common base amplifier, okay? So let's go through and figure out what our input resistance, output resistance, and voltage gain are for this guy with and I think without the early effect included. So let's start with without early effect. All right, so I'm going to draw my small signal model. Here's my base. Here's GM, oh, B pi, not R pi, excuse me. Here is my collector. And down here is my emitter. Now, I'm looking in through my emitter terminal, right? So that means that I would place my test voltage source, Vx, between the emitter terminal and ground, like so. And I'm trying to determine this current Ix, which is obviously just negative the emitter current that we would consider. So I do not yet have my emitter, or excuse me, my collector resistance in play here. So that is going to be between the collector and ground. So here is RC. And what do I place between the base terminal and ground? So this is a small signal analysis, right? Meaning that all of our DC voltage sources should be turned off. So between the base and ground for any common base amplifier, we have to have a short circuit inherently, right? For our small signal model. All right. So I'm going to redraw this guy a little bit to kind of help me see what's what here. So here's my emitter. Down here is my base. Between my emitter and my base, I have that resistance R pi, where the positive polarity terminal is on of V pi is on the base side and the negative polarity terminal is on the emitter side. Then let's see, between my emitter and my collector, I have my current source. The current's flowing from the collector to the emitter. So here's GM V pi. And then between my collector and base, I have my resistance RC. So anybody have any problems with how I've tried to kind of simplify this so we can figure out what's going on here? And this is my current, my test current IX. Everything seems hunky-dory here. All right, so I would argue that my current IX is simply the current flowing through my resistance R pi, which is going to be Vx over R pi, so that's current flowing down. And I will add to that my dependent current source contribution, GM times V pi, where V pi is the exact same thing as negative Vx. Everybody okay with that? So I can write this as Vx times R pi to the -1 minus GM, which means Rn is R pi to the -1 minus GM to the -1. And let's see, since R pi is beta over GM, we have GM over beta minus GM. Did I mess up a sign here? Let's see. So that's going to look like sorry, the textbook is telling me that it should just be 1 over GM. So I'm trying to figure out what silly mistake that I've made here. So if I look at my small signal model, Everything seems legit there, right? RC is placed between the collector and ground. My base shorted. Like I'm trying to figure out why it's not negative. Whatever, GM. My current is flowing from my collector to my emitter, so that's right. Negative there. So I have going down in this direction, Vx over R pi. Oh, I see what I did. Okay, there we go. So I applied KCL incorrectly. So this current plus this current should equal Vx over R pi, which is why I needed to change the sign on that guy when I moved it to the other side. So just a bad application of KCL, which puts a plus sign here, which puts a plus sign here, which puts a plus sign here, which puts a plus sign here. And since 1 over beta plus 1 is very close to 1 for large values of beta, this is approximately 1 over G. There we go. Right. Simple mistake. For our output resistance, we are going to draw our small signal model. So we have base, GM V pi all right, so sorry, that should be a C, not an E. So we're short circuiting our input voltage, right? Because we're finding the output resistance, which means that both the emitter and the base should be connected to ground in our small signal model. Then between the collector and ground, we have that resistance RC. And here is where we apply our test voltage Vx. Measure this current, Ix. And so we should be able to see very easily our value for our output voltage, or excuse me, our output resistance. What's it going to be? What's V pi? Here, let's start there. 0. So V pi is 0, then GM times V pi is 0, which means all that current Ix flows through the resistance RC, so our output resistance must simply be RC. And lastly, let's look at our voltage gain. So starting with my good old small signal model, So I'm saying the output resistance is the voltage drop over my collector resistance. Let's just verify that real quick. So in our original circuit, the output is the voltage at the collector with respect to ground, which is the exact same thing as the voltage drop over that resistance RC in our small signal model. So should be able to figure out some things pretty easily here, I believe. Let's see what we got. So V out should be negative GM V pi times RC, right? Because the current that's flowing into the positive polarity terminal of RC is negative GM V pi. Well, we can see pretty easily that V pi is just negative Vn, right? So negative GM negative Vn RC gives us a voltage gain of AV is equal to GM RC. So we have the exact same voltage gain as our common emitter core, but now we no longer have an inverting amplifier, right? What would happen if we included the early effect? We got 5 minutes and we can figure all that out pretty easily right here, right? So with the early effect included, that would place a resistor between the capacitor, excuse me, not the capacitor, or the collector and the emitter, right? So R naught, like so. So this one's going to be a little different. So how might we go about analyzing this guy? It's not going to be as simple as, or it doesn't look like it's going to be as simple as Kirchhoff's current law anymore, right? Because we have that other path. So what I would posit is that we can do something like this. So I'm going to do a source transformation here. And I'm transforming that dependent current source in parallel with R naught into a dependent voltage source in series with R naught. That's going to place R naught in series with RC. And it's going to give me a voltage source that is GM V pi R naught. Right here. All right, so what do I want to do now? Here's my current IX. So I'm going to have this current, let's call it IY for the sake of argument. And I know that this current, let's call it I pi for the sake of argument, flowing through that guy, right? So I know that I pi is equal to IX plus IY. which means that Ix is equal to I pi minus Iy. I pi is Vx over R pi, and Iy is Gm V pi, which is negative Vx R naught minus Vx divided by R naught plus RC. And now it's just doing the algebra to separate Vx from everything else. So we'll circle back around to that probably at the very beginning of class next time because we are out of time. All right, we can look at these other two guys pretty easily though. If we put our resistance R naught between our collector and emitter here, the output resistance is just RC in parallel with R naught. And we can see then that the voltage gain is just Gm times RC in parallel with R naught. So the only significant change from the early effect comes to the input resistance this time, which is interesting because it's exactly opposite what we saw in our common emitter. Early effect had no effect on the input resistance, the output resistance significantly. Here we see really doesn't do a whole heck of a lot to the output resistance, but changes our relationship for the input resistance appreciably. All right, I will see you guys on Friday morning.